The reduce function is another higher order function, like filter and map, that allows us to operate a computation over some list of input values. So let's take a look. A somewhat verbose but English expression of this idea is that we can be given an input list, right? So we've got an input list. This will be the first thing we need. And a reducer function, f, all right? So this will be the function we're passing in to our reduce function. And as a reminder, the reducer functional interface, a reducer from type T to U, is a function that takes in an initial memo value, and we'll talk about what this is in just a minute, named or of type U, and an item of type T. And it returns a value of type U. Now these types can be a little bit strange to process, but if we think of our input list as a list of type T, so a node of type T or a list of type T, the big idea of reduce is reduce goes from a list of nodes of type T to a single value type U that gets computed through the process of the reduce algorithm. And the last thing that the reduce function is going to need is an initial memo value, right? So we'll talk about this as well when we get to the code. And so what happens is we take this input list, and for each item of the input list, we give the current value of the memory and the next item to our function f, and then the result of that function f becomes the next piece of memory. So let's take a look at how this would be implemented recursively. And if we look at this reduce function implementation, notice we are going from a list of type T using a reducer of type T and U and some initial starting value memo. We're going from a list of type T to a value of type U. All right. And if we look at, if I number these the same as what we just talked about above, so this was part 1, part 2, and part 3. How are these things used? Well, we're going to see that the base case of reduce is when we get to the empty list, when we're done, the result that we're computing is going to be stored in our memo value, right? And so a very simple intuition here is, let's imagine we are reducing, and what we're reducing is an empty list, so just the empty list. Our reducer function f, let's call this the sum function that we looked at previously. This would just be a function that given two numbers returns to the sum of those two numbers, and our initial memo would be 0. So if we imagine what is the result of calling reduce with an empty list, sum, and 0, well, we can see that our base case is just going to return 0, which was our accumulated value, but at this point, no value's really been accumulated. So all of the work really happens in the recursive case. And what we're saying here is we're going to apply the same reduce process recursively to the rest of the items of our list using the same function. We're going to keep passing that same function down. And the memo that we're building up, this is the clever part of reduce, is taking the third parameter. Notice it's taking the current value of that parameter and the next value of the list that we're going to process, and computing the next step of this computation, right? So if this was sum and we had a sum of 1 and our initial memo was 0, we would be adding 0 plus 1, and then the next time we recurred, that value 1 would be passed into memo, and that would be the base case. Right? So I think this is an algorithm that makes a little bit more sense to look at visually because it does take some time to digest this recursive function call and get to what it means and how it is evaluated. But the idea is we are effectively computing the next value of memo and passing it in so that the next time reduce is called, memo is whatever the previous computational step was, and then we're moving forward on the list by one step each time we call reduce recursively, right? So let's take a look at a visual example here. So imagine a list 1, 2, 3, and our reducer function is this add function. We've got two parameters, the memo, which we've talked about, which is going to be the parameter that effectively is the result of the computation we've done up until this point. Item is going to be the next item in the list as we move through it one by one, right? Now, this is a very simple function. It's just adding these two values together. Right? And so what we're going to do is effectively reduce is going to say, okay, if our initial memo is 0, 0 plus 1 is going to be 1. And then we're going to say 1 plus 2, that's going to be 3. And then 3 plus 3, that's going to be 6, right? And so the reduce function is moving through the list and applying this reducer function step by step to each item in that list as it makes progress through it. So let's imagine this with a visual representation. This is our starting point. This is the first call to reduce. And what we're going to do is take the current memo, which was 0, we're starting from 0, and the next value of our list, and compute the result of our reducer function. And remember, this is a function that was passed in as a parameter to reduce. So we could use a different function besides add, but in this example, we're just choosing to use a simple add function. The result of that is 1, right? And so what happens is we take that 1 and we assign that to be the next memo value, and we move our list forward, right? And so now we're thinking about the rest of the list from where we had started, and we take the value 1 and the rest of the list, the next value in it, the first value of this list, and we add those two values together, which gives us a value of 3 is what the reducer would have returned. That 3 is going to become the next memo value in the recursive call to reduce. It's going to be passed in as the first parameter, and the rest of the list, the first value of it would be 3. Those two values get added together. And then we have 6 in our memo parameter for the final recursive call. And when we move and we reach the base case of this algorithm, whatever is the value of our memo at that point is the result of this reduce algorithm applied. Okay? And so if we wanted to think through this with some substitution, if we think what is the result of reduce with a list of 1, 2, 3 null, the add reducer, and an initial value of 0, well, we know that we're not going to reach the base case, right? We're not going to reach the base case. So what this will evaluate to, or what we could substitute this with, is a call to reduce on the rest of the x's using the function f, which is just being passed through, which was the add function, and then apply the reducer to our, using the current memo, which would have been 0, and the first value of our list, right, which would be the value 1. So we could substitute this reduce call is being replaced by, or it's going to be whatever is returned by its return value. And so we can think about, well, what is the reduce, what is the result of reducing a list of 2, 3 null with the add function with a memo of 1, right? Because that was the memo that was computed from 0 and 1. And this will be the memo that's computed from 1 and 2, right? So when we pass 1 and 2 to the add function, the add reducer, that would give us 3. So we would think that this call to reduce is replaced by, or is the return value of the next call to reduce, which we've moved forward in our list by 1. We're using this add function as the reducer, and the accumulated value here now is 3, right? Because what we're saying is pass 1 and 2 to add, and the result of that is going to be the next memo, right? Previously, the earlier step, we passed 0 and 1 to add, and that result was 1, right? And so what we're doing here is we are passing forward the result of adding up the next value and the current memo, right? So if we do that again here, we expect to take the first value 3 and the current memo 3, add those two together, and that would give us 6 to the next call to reduce. So let's carry this forward one more time. And so the last call to reduce that would be in this recursive evaluation is we take those two values, 3 and the next value of our list, 3, add those two together, and that would be the final memo here. Right? So 3 and 3 went to add, and that got passed forward to the final value of the memo parameter. And when we reach the empty list, now this will be replaced by, well, what is the return value when x is null? And that's just going to be memo, right? So we've reached our base case, and the value 6 is what this would evaluate to. And so that value would then, if we were thinking about this as in terms of frames on the stack, it's going to get propagated back up, right? And so it's going to be just returned all the way back up until we get back to the caller, and we've reduced this input list 1, 2, 3 to a value of 6 by using an add reducer. It added them all up. This was an example of writing a sum reduction. So let's try changing over to some code and working through an example reducer in VS Code. In today's lecture materials, you'll find an example OO reduce app, and go ahead and pull today's materials, start up the development server. And the two things that I'd like you to try and achieve here are, one, to declare a reducer function named max that is given 2 number parameters and returns the larger of the 2 parameters, right? And then in the main function, you're going to try and reduce the points list using that max function and an initial value of 0. So if I just very quickly move over to the code that you'll be working with, here's our input list. So we've got a list of numbers, and your first goal is to define a function named max here. This will just be a function that takes 2 numbers as an input and returns the larger of those 2 numbers as the resulting value. And once you've got this max function defined, you're then going to replace this initialization of result to not be 0, but instead be a call to the reduce function that reduces this input list using the reducer named max that you just defined with an initial memo value of 0. So pause the video here, see if you can't make this work, and once you do, the result should be the maximum number of this list, which if we were to scan this ourselves, we would be able to determine that 98 is the largest value in this list. Okay, so to define a max function, this is no different than we would have done before. Let max be a function, and I'm going to name these parameters to be conventional along with what we would expect in a reducer. So my first parameter is memo. This is the memory that's storing the built-up result as we reduce some input, and this is going to be of type number. And the next item in my list that I'm reducing is going to also be of type number in this example, and the return value is going to be number as well. And all I'm going to do is say if memo is greater than item, return memo, otherwise return item, right? And so this is the logic to choose of these 2 input parameters, which one is larger, and return the larger of the 2, right? As we showed in a previous video, we could be explicit about how we type this variable now. So notice max is a variable, and its type is reducer from number to number, right? And the functional interface reducer is defined down below in this example with the reduce algorithm implemented here in this recursive function, right? So now that we've defined that, and I should say that we don't have to be explicit here, right? By virtue of satisfying this functional interface of being a function that takes 2 input types, 2 input parameters of types u and t and returns something of type u, this function satisfies that functional interface, and both t and u in this example would be number. So if we wanted to say, okay, well, how do we use the reduce algorithm? So we're going to call the reduce function, and the first argument that we need to give it is our input list, right? So that's the list of values we're trying to reduce. Next, we're going to say, how do we reduce any given item into the current value of our computation, our memo, and that will be the max function, right? So we're saying, okay, max is going to be the function that we reduce by, and the initial starting value of this memo would be 0, right? And these are all positive numbers, so 0 would work here, but if we had all negative numbers, 0 wouldn't make sense to use. We would probably want to use like the smallest number we could, because 0 would have been bigger than all of them. So I'm going to save this, and sure enough, we get a value of the result is 98, right? If I were to make a number like 110 and add that number to my list, we can convince ourselves that this algorithm is returning or resulting in the maximum value of this whole list, Right? So why is this interesting? Well, I could also have an add function, right? That says add, the memo is going to be number, item is going to be number as well, and we're going to return a number. And I'm just going to return memo added to item, right? Or take the current value of our built up computation, the current sum we've added up so far in our list, and add it to the next item in our list. And instead of calling max here, I could use add, and this will compute the sum of all of these numbers, right? And notice there's to reduce this input list down to either the sum of them or the largest of them, and there are other reducers you can hopefully imagine. All I needed to do was replace, well, how do we give the reduce algorithm the logic it needs to perform the next step of this computation? And the next step of the computation is, well, what is the current value of the computation we've computed up until now, and the next item that we're going to compute with, and what reduced value or what accumulated value will we return in response? And you can see that this reduce implementation is achieving that by taking the current memo, which we started from 0, right? This is our current accumulated value, and passing that to f, which is our reducer, along with the first value of our list. And then that is going to become the next memo as we continue applying this process down the list. This is very similar to another concept that you've seen and become familiar with, but this is the recursive implementation of it. Right? So I just want to very quickly convince you that this is no different from saying, let's imagine we have some array A, and A is 1, 2, 3, and we have some memo, I'm going to call it, that will be our result value. Memo is 0 initially, and we could write a loop, something like for let I be 0, I is less than a.length, and I++, right? And I would need a curly brace there, but I've run out of screen space. And so we could say, okay, the next value of memo is going to be assigned the current value of memo plus a index I, right? And then we could return memo if this were inside of a function. What I want to convince you of is that this process here of saying, okay, let's take the next element of our list, which we're doing by incrementing this index variable by 1, and perform some computation. We're going to add the current resulting variable, the current variable where we're accumulating a result, add those two things together in this example, and reassign that back to memo. The key difference here is that in this higher order function, what we're saying is, you know, this logic is hard coded in to any of the algorithms that we've done that sort of met this pattern before. So rather than doing that, why don't we allow you to pass in some reducer function f, and you can define how this step works. And f is going to be given the current memo and the current value of I, right? And now we can say, well, however you want to accumulate your result, given the current value of our computation up until this point, and the, oops, this should have been a index I. That's my bad. A index I. That's the next item in our list. How do you accumulate those results and then take whatever the result of accumulating the next value of that result and say that, okay, that's the next memo, right? But this one step of indirection, we could say, even though it feels a little bit more complicated because we're making a function call, remember, ultimately, if that function is a very simple function, such as memo added to a of index I, this is no different from the same process we've seen before. We're just creating an abstraction around it in the form of a higher order function. And in this example, you're seeing a recursive implementation of it. Right? So this is the reduce algorithm, and it helps us take a list of values and accumulate some resulting value out of that. And oftentimes you'll see values of the same type being accumulated to a single value of the same type. But this U could also be an array. Like we could write a function that reduces by appending values to an array. We could reduce a list to an array if we wanted. We could reduce a list to another list. We can be pretty clever with how we think of this type U. It doesn't have to be a single value, but we'll look at more advanced examples shortly. Next, we're going to turn our attention to function literals that make working with higher order functions like filter, map, and reduce even more ergonomic and user-friendly.